this video, we're going to be talking about the radioactivity, and we'll talk about why some elements undergo nuclear reactions or why some elements are radioactive while others are not. In addition to that, we'll talk about different types of radio decays and do some examples along the way. So starting out with, let's talk about the stability of a nucleus. So the stability of a nucleus is actually dependent on the ratio of the neutrons to proton. So I have the ratio here twice. So let's say the symbol for the neutrons is going to be N, the symbol for protons is going to be P, and it's all about the ratio of neutrons over the protons. For a lighter nuclei, the ratio of the neutrons over protons is close to 1, and there are a few exceptions where it's a little bit less than 1, but it's roughly close to 1. But as the mass of these nuclei increases, or another way of saying as you go on to these higher elements, then the ratio is going to increase up to 1.5. So it's going to start going up from, it's going to be greater than 1, but then it's going to be less than 1.5. So that's what put them in the order of stability belt, or another way of saying, as long as the ratio is not 1.5 or it gets bigger, or if it gets smaller than 1, that's when you're going to have an issues with the element, and as a result, it will start showing some radioactive decays. Now, just to kind of refresh our memories, make sure you know how to write down the nuclear symbol. So in a nuclear symbol, you're going to have the element. So suppose the element is going to be X here, so that's your element symbol. And then you're going to have your number of protons, or the atomic number, on the bottom here. And then you're going to have a mass number on the top. So this A represents the mass number. And then Z represents your atomic number, which is the same as the number of protons. Now also keep in mind this Z, let's write down here, number of protons. Then also keep in mind that A is actually going to be equal to the number of protons plus the number of neutrons. So that's how you really find the mass number. Now let's talk about, if the element is indeed radioactive, what kind of decays it can undergo. So there are technically 4 to 5 different types of decays you could see in a radioactive element. The first one is an alpha decay. The symbol is just going to be letter alpha, and it's just going to be in a helium nucleus. So whenever you are doing an alpha decay, that means you are going to be losing in a helium nucleus, where you're going to have 2 being the atomic number and 4 being the mass number. So another way of saying, what you're really losing here is 2 protons and 2 neutrons. Because remember, the mass number is 4, so it has to be total of 4. So the number of protons plus the number of neutrons should add up to the mass number here, which is 4. So that's one of the things you want to make sure you know, what you're really losing in a particular decay and how that symbol is going to look like. We'll talk about a beta decay. The symbol is going to be this letter beta, and in a beta decay, you're going to be losing a neutron. So you have a neutron, and that's going to be lost to a proton and an electron, and that's one of the reasons why you call it an electron decay or a beta decay. So it's, when I go ahead and write down the symbol, it's going to be an electron. So you lose an electron, so you write down -1 here. And since you lose a neutron to a proton, and even when you lose the neutron to the proton, your mass number really doesn't change, because remember, the mass number is going to be the protons plus neutrons. So if you do lose the neutron, you're actually losing that to a proton, so your mass number really doesn't change. So that's another important thing that's usually asked, in what particular decays the mass number doesn't really change, but it only changes the atomic number. And one of those is going to be the beta, or the electron decay. let's talk about positron decay. The symbol is just going to be P. And it's just the opposite of a beta decay. So it's going to be an electron. It's got +1 and then a 0. So in a positron decay, a proton is going to be actually converted to a neutron plus a positron. So I'm just going to write that down, positron here. And you may wonder now what really positron is. But positron is just a type of subatomic particle. It's going to have the same mass as that of electron, but it just have a positive charge. That's all really it is. So when this positron really, when this proton rather gets, I'm going to write that proton here. When this proton gets converted to the neutrons and positron, the neutron stays in the nucleus and this positron goes outside the nucleus, and that's why you have a +1 there. And as a result, your mass number still doesn't change because your proton is changing to the neutron, so there is really not any loss in terms of the overall mass number. The neutron decay, as the name specify, it's going to be a loss of neutron, and clearly we can see it's going to be 0 and 1. So there is no change in the atomic number, but you will have a change in the mass number. So this is one of the decays where the mass number changes, but your atomic number doesn't really change. The last one is called a gamma particle, so just called gamma, it's a Greek letter. And the gamma decay is really nothing but just a possible rearrangement of the protons and the neutrons. So what happens sometimes, you do have the right number of the protons and the neutrons to get the ratio that you really want for a particular nuclei, but then their arrangement may not be very stable. So when their arrangement is not very stable, they may rearrange themselves. And when they rearrange themselves, they emit some sort of energy or particle, and that's called the gamma particle. Now, out of all of these guys, your gamma decay is going to be the most dangerous. All right, it's going to be the most dangerous in terms of the energy. And if I want to compare the rest of these guys, the alpha particle is usually considered to be the least dangerous, but then the most important is obviously going to be who is the highest energy carrying particle, and that's going to be your gamma particle. So there are actually even more dangerous than the X-rays. So you guys aware of how X-rays work, they can't really pass through a very dense medium such as bones, and that's how you get the structure of the bones using X-rays. However, these gamma rays, they are actually even stronger than X-rays, and they will pass through a very dense medium such as bones as well. Now, to really save yourself from the gamma rays, you need to have a really thick concrete wall or a thick lead jacket, and that will save you from the gamma rays. As far as the alpha rays go, since they are so weak, you can just put a paper in front of the alpha rays, and that will probably block the alpha rays at that point. Okay, let's talk about some of these examples and let's learn how to really write these nuclear equations. They are not that bad in terms of understanding. It's as long as you know how your decay gonna look like, it's all about balancing the mass number and your atomic number. So those are the two things you have to make sure you have your mass number and your atomic number balanced. So suppose this first one is saying I have this uranium-238, so that's another way of writing in a nuclear symbol where you're not really given the atomic number, and that's because you can go back and look in the periodic table and figure out what that atomic number is going to be. Now, this uranium-238 undergoes an alpha particle. Well, the very first thing you probably want to do is just go ahead and write down your alpha particle, which we know is going to be helium. So it's going to be 4 as a mass number and 2 as your atomic number. And the rest, I really need to balance it out. So when we say balance it out, means I want to make sure I have a total of 92 for your atomic numbers on the product side. So since you already have 2 coming from the helium, I need to have 90 here. And then as far as the mass number go, how much mass number we need here? we need a total of 238, and we already have 4 coming from the helium. That means this must be 234. And then once you kind of figure out your atomic number and the mass number, your element is going to be based on what the atomic number is. So then you go back in the periodic table and figure out what that atomic number going to be. So 90 atomic number is going to be for the thorium, so it's going to be the TH there. So remember, another important fact in nuclear reactions, you learn that the mass is really not conserved, or the matter is really not conserved. You can create a different element. That does not happen in chemical equations. When you do chemical equations, you're not changing a carbon to a nitrogen. However, when you do nuclear reactions, you could technically change a carbon to a different nucleus, to a nitrogen or something else. That's exactly what happened. Now, every single nuclear equation that you're going to have will have some sort of mass loss. When you're going from the reactants to the products, even though we kind of balanced out these mass numbers and atomic numbers, there's still going to be some mass loss. And whenever you have a mass loss, that mass is going to be converted to the energy, and that's the energy that's used in a lot of areas, such as atomic bombs or the sun producing energy based on these equations, or even the radioactivities used in medicines as well. Let's talk about some other examples here. So it's probably going to be a good idea to pause the session here and figure out these next few reactions and see if you understood those. So assuming you did pause the session and did work on the next of these, some of these reactions. So let's see if they matches with mine. So I got this nitrogen nuclei, which is 15, and then it's undergoing a beta decay. So what I want to do, I know that my beta decay looks like -1 here, 0. So in the beta decay, remember a neutron gets converted to a proton and an electron. So you do have an electron here, and now it's going to get converted to an extra proton, and that's why you're going to have an 8 here. Now, if you do forget that, keep in mind your atomic number needs to be same on both sides. So since you have 7 here and you wrote down -1 here, then you must have 8 here in order to have a total of 7 on the product side. Your mass number really doesn't change, so that will still be 15. And then you go back in the periodic table and check who really has an atomic number of 8. And it turns out that's going to be your oxygen. Okay, what about this next one? Oxygen undergoing, well, I got a wrong one here. It's actually carbon 14 undergoing a positron decay. So when carbon 14 undergoes a positron decay, that means I'm going to have an E plus 1 here is 0. And when you have a positron decay, what really happens, a proton gets converted to a neutron and a positron, and that's how you lose this positron. And when I go ahead and write down these values here, it's going to be 5 here, because 5 plus 1 is going to make a 6, and the 5 is the mass number doesn't really change. It's still going to be 14, and that's just, and look in the periodic table who has an atomic number of 5, and that's going to be the boron. You know, it may not exist in nature, but this is more like understanding purposes. Okay, what about this next one? What's really going on here? So sometime you may be asked questions where you're missing a particle and you got to fill out what type of decay that particular element's going to be. So it seems like I have 13 here and I have only 12 here, so that means I must have one extra atomic number here to make up a total of 13. Your mass number is really not changing, so that means it's going to be 0 here, and now it's going to be easier to recognize what type of decay that's going to be. Well, that's clearly going to be a positron decay. Let's talk about 2 famous processes that really happens in nuclear reactions. The first one is called a nuclear fission. As the name specifies fission, you will have a large nucleus breaking into 2 smaller nuclei. Now let me take an example of uranium-235. Now this uranium-235, we know it's radioactive, and if I want to make sure this undergoes the nuclear fission, I must stimulate it, or another way of saying, you must initiate this fission reaction. You're not going to have this uranium-235 just sitting on the table and undergoing this nuclear fission, but rather you must use a smaller particle such as a neutron, and that's also called a bombarding with the neutron, so that it can initiate the process of nuclear fission. Now, when that happens, it's going to break into two smaller or maybe more than two nuclei, and it's going to produce a lot of energy that could be used um, in a bad way or also in a good way. Now, it's when you trying to figure out what's going to be the other particle here, all you really got to do is just balance out your atomic numbers and your mass numbers. So your atomic number here is going to be a total of 92 on the reactant side, and let's see what the atomic number we got on the product side. We're going to have just 36 here because the neutrons doesn't really have an atomic number. So when you subtract 92 minus 36, we get 56, so it's going to be 56 here. And then we're going to do the same thing for the mass number. So on the reactant side, your mass number is going to be 235 plus 1. So write that down, 235 plus 1, that's going to be 236. And then on the product side, you can clearly see I have 91, and then plus, I got 3 neutrons. Each neutron has 1, so that means plus 3, so it's going to be 94. Now, when you subtract 236 from 94, it's going to give you 142. All you really got to do is just go back in the periodic table and figure out what element has an atomic number of 56. And it turns out it's going to be the barium. All right. So, you know, the krypton, the barium that you produce, they may very well be radioactive as well. And if that's the case, they may very well break down into further nuclei. And in that case, you kind of processing a chain reaction where in every nuclei you produce, it may be unstable and it gets broken down into another nuclei until, and the process is going to keep going on until you get to a stable nucleus. And every single step in those nuclear chemistry involves a mass defect or a loss of mass, which converts into an energy. All right, so when this converts into an energy, over time it could have a very large amount of energy, and that's how these a lot of these nuclear bombs work. What about this nuclear fusion? In a nuclear fusion, you have these smaller nuclei combining to make a bigger nucleus or a relatively bigger nucleus. And one of the common examples I want to talk about is what happens inside the core of Sun. Now remember, the Sun has a lot of hydrogen, and the hydrogen's isotopes combine together to make helium. All right, so when this 1H3 and 1H2 combines together, they're going to be making a helium there. So it's going to be helium. And remember, the helium is going to be 2 and 4. Remember, helium is a stable nucleus, and that's one of the reasons why you can make the helium here. And then make sure your atomic numbers and the mass numbers are balanced. So you do have a 2 atomic number here, a total. The mass number here is going to be 5. So when you add this up, well, I should have 1 here and 0 here. So that means there is a production of a neutron as well when you're doing this nuclear fusion inside the core of Sun. The nuclear fusion process produces a lot of energy, and this is the energy that comes down to Earth. That's how you're going to be balancing all these nuclear equations. Make sure you have your mass numbers and atomic numbers balanced, and based on new atomic number you get, figure out what's going to be your new element produced. And if you have any questions, feel free to leave any comments in the section below.